Mechanistic problems often involve really complicated sort of conventions and stuff like that. And to help you with these problems, I have created a video back in the resonance days that helped you think about how to draw these arrows and such. But Professor Miller has a handout, and we'll discuss that in some greater detail. So this is the Miller handout I was referring to, and here are his instructions for how to do a mechanism. And you will recognize many of these instructions as the kinds of things that showed up in that mechanism and resonance video that I did earlier. And in particular, things like getting to use the starting material as many times as you like is something that shows up in his handout, and showing all the intermediates and describing all resonance forms, using arrows that start from electrons and go to where the electrons go. All of these should be familiar to you by now. The equilibrium arrows step is itself a video, and then of course in the remainder of this video what I'm going to do is walk through this mechanism down here. The core message from this part of the video is going to be this: strongly resist as much as you can drawing O- ever, as long as you're using acidic or neutral conditions. It is possible to imagine acidic, like sulfuric acid, has oxygens in it. You really want to resist drawing O- ever if you have acid or neutral conditions. By contrast, if you have basic conditions, you never want to draw O+. And again, it's not a hard and fast rule. There are exceptions and so on. But as much as you can, resist drawing oxygens with pluses on them when you have base around, and definitely resist drawing oxygens with minuses on them when you have acids around. And if you just keep that in mind, then mechanistic work will go more smoothly. In the Miller handout, one rule that I would add to it is if you see a reagent over the arrow, you will find it helpful to draw out that reagent as a good Lewis structure. So in other words, rather than simply having HCl, I will go ahead and draw it as H bond Cl. And the reason for that is it becomes helpful when you go to draw out the mechanism. And likewise, this right here I've currently drawn as an OH, but it's not a bad rule to simply erase that and draw out the bond. It's also not a bad idea to go ahead and draw in any lone pairs. And drawing out explicit hydrogens in lone pairs are a great way to get unstuck if you are stuck in a mechanism problem. So if you have a reagent that looks like this, drawing that out in its Lewis structure form might spark something. If you have implicit hydrogens buried and you're stuck, one good thing that you can do is just start drawing the implicit hydrogens, make them explicit, and maybe that'll spark something. Or draw in lone pairs, and then maybe that'll spark something. But what we have here is a strong acid. What we have here is something that is not yet a good leaving group, but could be made into a better leaving group than it is, as long as we do this kind of protonation. And so you have to start this mechanism by using the strong acid as an acid. And keep in mind, of course, that since we have a strong acid present, you know that we're under acidic conditions, and at no point will I want to draw an O-. In other words, if you were tempted to start this mechanism by having the oxygen leave, that's a really bad idea, and you shouldn't do that. There's at least two good reasons for it. One is that it would form OH- if you did that. And again, we're in strongly acidic conditions, so that's not something you should draw. But the other main thought here is that OH- is a terrible leaving group in and of itself. The pKa of OH- is 16. In other words, it's not a good leaving group. The leaving groups that are decent are negative pKa's. Now that I've drawn those red things, it's time to make them go away and never think of them again. Now, of course, I have a positively charged oxygen, which means that when this leaves, it leaves as just plain water, and obviously that's okay. The pKa for this group is on the order of -2. Again, the pKa of the OH leaving would be about 16. This being negative means that it's plausible. Water is not a particularly good leaving group, but it's at least a plausible leaving group. You have now generated a cation that's tertiary, so reasonably stable. I failed to draw it out here originally, but there was a Cl- that's floating around as a result of that first protonation step, and that can now serve as the nucleophile and finish off the mechanism. This molecule is achiral, so I'm not specifying its stereochemical outcome. If this were a simple predict the products type thing, you wouldn't necessarily need to draw out this mechanism, but if you're working with the mechanism, I strongly advise you to draw out the Lewis structure to begin with, and even if all you're doing is a predict the product sort of thing, drawing out the Lewis structure may help spark some ideas. The key feature of this mechanism, as far as I'm concerned though, is in the presence of a strong acid or a neutral, I don't want to draw an OH-, so I have to do the protonation step first in order to make this into a better leaving group, so that when it leaves as the neutral species, which leaves behind a cation. If at any point in this mechanism you draw an O-, you are wrong, and this is a invalid mechanism. Unlike our previous mechanism where there was some challenge getting going, in this particular mechanism, most students will not have any challenge whatsoever in identifying what happens first, which is the leaving group needs to leave. You have a secondary chloride that will leave. Where students might run into trouble is what happens at this stage. And again, my advice is go ahead and draw out any Lewis structures with explicit hydrogens on the OHs and NHs and things like that, and draw in any lone pairs. And what I'm hoping that you'll spot here is that since this oxygen contains a nucleophilic lone pair, and since we are surrounded in a sea of ethanol, because ethanol is the solvent here, that the oxygen can simply go ahead and make a bond in the first place to the secondary carbocation. I have not drawn any stereochemistry at this position because, again, this is going to be an achiral molecule, but I have drawn this positively charged intermediate. And this is a case where I'm not using a strong acid at all. In fact, there's really no acid, but there's really no base here. This is purely neutral conditions. And so it is okay to draw the O plus species in neutral conditions, but you don't want to draw any O minuses. I now have another ethanol molecule floating around nearby, and it can come by and perform the key deprotonation, which will then lead to the final product, which is this isopropyl ethyl ether. The pKa of this group as drawn is about -2. The pKa of the protonated ethyl byproduct is likewise about -2. And so there's no energetic barrier to get over here. This is a smooth process. So chlorine leaves, ethanol attacks, ethanol then attacks the protonated ethanol, pops the hydrogen over. There's no energetic penalty there. That is the main final product for the compound that you care about, and this is the byproduct that you don't care about very much. So where the problem would arise for students in this particular mechanism, and where students would go wrong, is if they tried to use this chloride right here to perform a deprotonation step. And the real problem with that idea is that you end up forming this O- structure, and you do that at the same time that you're generating HCl. But of course you know that Cl- is the counterion of a strong acid, so the pKa of this, of HCl itself, you know as -7, and the pKa of this is 16, whether you're thinking in terms of the O- or the neutral species. And so the gap between those two numbers is 10 to the 23rd. So this is 10 to the 23rd in the wrong direction. The Cl- is not a strong enough base to pull off this deprotonation. Or prefer to think about it the way I do here, which is you do not ever want to draw an O- as long as you're talking about a neutral solution, like just plain ethanol with neither acid nor base in there. This is generally a good rule because of how much easier it is to put a hydrogen on an oxygen than it is to pull a hydrogen off under neutral conditions with the kinds of acids that we're going to have floating around. So again, Cl- nowhere near strong enough base to do this subtraction. It's not even in the same ballpark. Whereas ethanol is absolutely a strong enough base to remove this because it'll just share it with other ethanol molecules on down the line. Don't draw O- if you have strong acids around or neutral conditions. And generally speaking, don't draw O+ if you have basic conditions around. I'm not going to walk through a mechanism with a base, but just imagine, as I'm saying it, that you have, say, a sodium hydride or something like that, and you're trying to do a Williamson ether synthesis. If you have a base explicitly present, then that will start by removing a hydrogen, and then you're going to have O-, you're not going to have pluses, and the O- will carry through. And then it's okay to have neutral oxygens and minus oxygens, but it won't be okay to have positive oxygens as long as basic conditions are present. The main reason why I'm not going to illustrate one of those mechanisms is because at this point we're going to be doing more work with the acidic and the neutral mechanisms.